Up next is hydroboration. What is hydroboration? An alkene or an alkyne reacting with a boron thing, like BH3. When BH3 reacts with this alkene, it says you get 94% this thing, 6% that thing. Let's dissect it. So this says when one hexene, there's hexene, reacts with BH3, we get 94% of the hydrogen added to the more substituted carbon, and the boron added to the less substituted carbon. So at first glance, that looks like an anti-Markovnikov addition. That's what we are going to call this one, an anti-Markovnikov addition. The hydrogen goes to the more substituted side, which is not the way Markovnikov describes stuff. Why does it work like that? Well, in the mechanism, you're concerned with who's the electrophile. In BH3, first of all, boron is less electronegative than hydrogen, so dipoles are actually pointed toward the hydrogen. That has not been the case in any of our examples so far. Dipoles pointed toward the hydrogen and away from the boron. As well, boron is a moron. Boron is a weird molecule that it has no formal charge when it has 3 bonds. So boron has less than an octet in this molecule, so he would like to get some electrons. So if we give boron some electrons, the boron would become negative. That's not super great. So simultaneously, at the same time, this is a concerted reaction. Those 2 arrows, those 2 things are happening all at once. The hydrogen, with its electrons, attacks here. That's the hydrogen, the hydride, acting as a nucleophile. I have made the statement, and I stand by that statement. The nucleophile attacks the better carbocation character side. Always and forever, the nucleophile attacks the better carbocation side. In previous reactions, the nucleophile was sometimes bromide. It attacked a carbocation. The carbocation formed on the more substituted side. Water attacked the carbocation. It attacked the carbocation that was formed on the more substituted side, the more stable side. When we had the bromonium, when the nucleophile busted open that bromonium, it attacks a more carbocation character side, more substituted side. Have I said this enough? When we had the mercurinium and the water busted open that mercurinium, it attacked the more substituted side, the better carbocation side. I should go ahead and make a little note. I keep saying more substituted, but I mean more stable carbocation side, better carbocation character. If we had complicated alkenes that have like resonance or induction, we have to attack the better carbocation side, which may or may not be more substituted, because resonance and induction changes the game a bit. Okay. Anyway, hydride with its electrons attacks the more substituted side, and that's how we ended up with the boron added over here. Oops, that's at H2 now. And the hydrogen added over there. Yeah. This says it's 94 to 6%. We're going to pretend that 6% version does not exist. If it were something like this, where one side is a primary carbon and one side is a tertiary carbon, the scales are tipped even further toward the anti-Markovnikov, toward the 94%. We would get this as our almost exclusive product, legitly, but we're going to say even this is exclusively the product we get. Sure, you get a little bit of the other stuff, but we're going to say boron does anti-Markovnikov. Okay, this is called hydroboration. Hydroboration means making an organoborane. A few words about making an organoborane. It's addition of borane to an alkene. Borane, that's BH3. Yeah. It could be an alkene or an alkyne, actually. The first step in preparation of alkenes and alcohols, among other things, alkanes and alcohols, sorry. Alcohols we will see momentarily. B2H6 is a dimer of BH3. It reacts the same way. So even if you see an arrow that says B2H6 over it, draw the mechanism like it's BH3. Or there are other things that behave like BH3, such as a BH this thing. That's isobutyl boron. It's just a boron that has been made more bulky. Why might you want to make the boron more bulky? Well, the more bulky this boron group is, the smaller this percentage becomes. So if you make the substrate, the alkene thing, more bulky, you get more of the anti-Markovnikov. But also, if you make the boron thing more bulky, you get more of the anti-Markovnikov stuff. But we're going to say it always makes anti-Markovnikov anyway. So sometimes you see a boron that has a single hydrogen and some other legs of any type over here. There's something called 9BBN. 9BBN is this thing. That thing's a little bit hard to draw. This big ring down here looks like a banana, so sometimes it's called a banana boron. Yeah, banana borane. Yeah, weird, I know. But 9BBN, that's this. It's a big, bulky boron to try and ensure that you get all anti-Markovnikov addition. Okay. So, let's draw the mechanism of this guy. We said if it starts out with B2H6, we're going to pretend it's just BH3 because B2H6 is just a dimer of BH3. So mechanism-wise, alkene attacks the boron. At the very same time, a hydrogen with its electrons attacks back. We end up with this thing. This thing is an organoborane. I did not have to draw that hydrogen out explicitly, but I chose to just to make sure you're following along with where that hydrogen is. Organoborane. Done. Well, really, BH3, there are 3 hydrogens that can do this attacking. So really, if there are 3 hydrogens, this step happens 2 more times to replace this hydrogen with a big alkyl group and this hydrogen with a big alkyl group. Something like that banana borane looks appealing. Something like this borane looks appealing because it only has 1 H. It means you would only have to do the reaction 1 time. So actually, on the fly, I'm going to change our borane to not be that kind and have 2 hydrogens. I'm going to shortcut our mechanism to be that diisobutyl borane. Got real squishy over there. These hydrogens don't exist anymore because we just changed it. And this is a diisobutyl. What's the reason for making a diisobutyl? So that our mechanism is a little bit shorter. If you did BH3, the first step repeats 3 times to end up with 1 boron, and 3 of my alkene groups reacted with it. So this intermediate is called an organoborane. That's what it took when you did the first, that's what happened when you did the first step. Adding B2H6, you get an organoborane. Once you have that organoborane, that's when you add the next stuff. The next stuff in this reaction is hydroxide and peroxide. Hydroxide and peroxide will be an oxidation reaction. So this reaction specifically is called hydroboration oxidation. Hydroboration oxidation. That's our 2 separate steps, our 2 separate sequences. So once you have hydrogen peroxide and hydroxide in solution, a little side reaction happens between those. Hydroxide takes a proton from peroxide to make you some water and some OOH with a minus on that O. Ooh, that's weird. That OOH attacks the boron. Remember I said boron is a moron. He does not have an octet. And he's grumpy about not having an octet, so he wants more electrons. He's a good electrophile. So we gave him more electrons in this reaction. But now he says he's making too many bonds. That's not good enough. He wants to make fewer bonds. So the migration step that happens next is kind of like a carbocation shift. It's kind of like that. It's different, but it's kind of like that. the gist is boron says, I'm making too many bonds. I need to make fewer bonds now. So we migrate. The carbon-boron bond becomes a carbon-oxygen bond. Carbon is no longer connected to boron. So carbon will now be connected to oxygen. But if that's the only arrow I drew, we would explode oxygen's octet. So I could end up breaking this bond as well. Peroxide bonds, that's what an OO single bond is, not very stable. Check it out. Peroxides, truckers on the highway, OO bonds, not very stable. Peroxides are explosive compounds because OO bonds, not very stable. Make you say, uh-oh. So I migrate my bond from carbon to oxygen. I let go of a hydroxide, and my oxygen is still connected to the boron thing with the spider legs over there. Okay, we satisfied boron by taking away one of his bonds, taking away his negative charge. Now the boron says, I'm still not satisfied. I've got not enough electrons. I don't have an octet. So the hydroxide we kicked out comes back to try to help out this boron who's on the struggle bus. Boron is now connected to my OH and the little legs that I really did not plan spatially well for. That boron is now negative because he's making 4 bonds again. I'm ready to be done with boron. Aren't you ready to be done with boron? Let him go. Let's just let boron float away on his own and do his own thing, and let's rescue our carbon group from the boron. So we turned loose from that boron, let it go, and we get an O-. The boron, after he turns loose, is likely to react with some more hydroxide and water and stuff like that in solution to become a borate, a boron with a bunch of oxygens connected. We don't care so much what happens to the boron, so we're just going to send him off into the oblivion and pretend he doesn't exist anymore. So we've got our compound that has a minus, and that's not our final thing. That's not our final product. The final product takes a proton from water. We have a little bit of water in solution. Water is probably the solvent of the second step. But anyway, we have a little bit in solution where peroxide and hydroxide reacted together, and we get this alcohol product. Ta-da! Alrighty, are you ready to talk stereochemistry of this reaction? Well, these two first red arrows are happening at the same time. It's concerted. So because I'm reacting with an alkene that's trigonal planar, that planar alkene has to react on one face or the other with this boron. What does that mean stereochemistry-wise? It means the H and the B undergo syn addition. Syn addition. The boron and the H are added to the same face, whether that's both added pointed up, as I have drawn, or both added pointed down, as I have omitted. That methyl has to move out the way in order for that hydrogen hydride to be added to that top face. So this is a syn addition product. What got added syn? The H and the boron got added syn. Okay, so if we continue on down here, the H is still there and it's still syn. The boron is still there, it's still syn. The methyl is still back yonder, out of the way of the hydrogen. When you do this corner migration step, that migration happens with retention of configuration. This carbon, that specific carbon, is not involved in the reaction. The electrons are transferring from the boron to the oxygen. Carbon was not participating there. What that means is the oxygen is still pointed the same direction that the boron was pointed. So if I fill in my hydrogen again and my methyl, and I continue on down because no more reactions happen at that carbon, hydrogen is syn to the OH in the end. Hydrogen is syn to the OH in the end. I'm almost there. Hydrogen is syn to the OH in the end. Yep, like that. Well, this is if the borane added to the top face, we get that product. If borane adds to the bottom face, what do you get? The enantiomer. Hold, please. The enantiomer of that thing looks like this, where the methyl is wedged and the H and OH are dashed. It's a syn addition product. Hydroboration oxidation gives you a syn addition product. But, if you just start repeating that, what is it that gets added syn? The H and the OH get added syn. If you actually looked at the layout of this molecule, the methyl and the OH are anti. The hydrogen and OH, which are the two groups that got added through this reaction, it's those two things that are syn, but sort of by default, because those added syn, the methyl and OH are anti. Okay. There's my product. Would you expect the product as obtained in this reaction to be optically active? No, because it's a racemic mixture of enantiomers. Draw the product in its most stable conformation. Yep, conformations. That's a six-membered ring, and conformations of six-membered rings, that means chair structures. So if I tried to draw that guy in a chair structure, if I look from my blue eyeball over here as standard protocol, based on what we've learned, that methyl is on the back carbon going down, that OH is on the back carbon going up. Yeah? That's not the most stable conformation, because both of those groups are axial. So if I did a chair flip, I would end up with both of those groups being equatorial. You can't put all that old knowledge by the wayside. It's still all relevant, unfortunately. So overall, this reaction gave me an anti-Markovnikov addition. That means the hydrogen went to the side with fewer hydrogens. It gave me a syn addition product, but what got added syn? The H and the OH, and this product would be considered trans. That's because if you consider the two hydrogens attached, those two hydrogens are pointed opposite directions. It is a trans product, even though you did syn addition. Confusing, I know. The regiochemistry is anti-Markovnikov. The stereochemistry is always syn, because the boron is replaced where it stands. That means when you do that weird migration, the boron and oxygen, the oxygen ends up pointed the same direction that the boron was pointed before the migration. Yeah? What we just did was called hydroboration oxidation. We did hydroboration oxidation. That's the most important reaction of organoboranes. But when you have organoboranes, you can do other reactions with them too. That's those other guys. Protonylysis is when you react with an acid to replace the boron with a hydrogen. Oxidation is when you react the organoborane with hydroxide and peroxide to replace the boron with an OH. Bromination is when you react the organoborane with Br2 and a base in order to replace the boron with the bromine. It's real hard to say those the right way. But this one we've already done. Let's see one of those others in action. Oh, I forgot. This is actually the set of reagents. This is an acid. That's the protonylysis one. This is Br2 and a base. That's the halogenation one, bromination one. This is the hydroxide and peroxide oxidation one. We've already seen that one. It makes an alcohol. So this slide says, beware of deuterium labeling. What? This is BD3. What is D? D is deuterium. Deuterium is heavy hydrogen. Hydrogen that's not just one proton and nothing else, or one proton and electron. Deuterium is one proton and a neutron as well, so it's heavy hydrogen. When you add BD3 to that molecule, you get a D in the armpit and a BD2 here. That's your organoborane part. Remember, it does syn addition. So we have our two groups that got added. They are syn. Then when I do my second bit, this stuff, that's a carboxylic acid. But that carboxylic acid has a T over there instead of an H. What is a T? That's a tritium. You've heard of it if you've ever seen Spider-Man. Tritium is a hydrogen that's heavier than a deuterium. Tritium is not as common, but yeah. What I do this time is replace the boron with a hydrogen. Are we drawing the mechanism for this reaction? No. We're drawing the product and only the product. The boron is replaced where it stands. What does that mean? Boron was wedged, tritium is wedged. That's one of my products, plus I will get the enantiomer. Do you have to know the mechanism for how the hydrogen replaces the boron in this red example? No. Do you have to know the hydroboration oxidation mechanism that we did at first? Yep. Okay. So here's a nice little tiny summary of some of the reactions we have covered so far. These reactions are predict the product reactions. What that means when I ask you a predict the product type question is draw all products, including any rearranged carbocations and stuff like that. Draw all products, including stereochemistry as well. It does not mean draw curved arrows to show me all the mechanisms, all the intermediates, all the stuff, final products and final products only. But in order to get the predictive product questions right, you often have to think through the entire mechanism. So I'm not looking for the whole mechanism for you to draw it, but you often have to think about it anyway. All right, let's get to it. I think you're probably feeling most confident about this bottom right reaction, so let's start there. So we're not going to walk through the whole mechanism, but I'll talk you through it a bit. We're not going to draw it all. Alkene reacts with HBr. That's an acid addition to an alkene. It's going to go through a familiar intermediate known as a carbocation. Carbocation is going to form on the primary carbon or the tertiary carbon. Obviously, the tertiary carbon. Then bromide is going to attack, and we get that. That is our one and only product. This product has no asymmetric carbons, so I do not have to worry about dashes and wedges. I get to leave it alone as is. I think you're probably next most confident about this one. In the bottom left corner, that's acid and water. That's acid catalyzed hydration. Also goes through a carbocation. You're going to make a tertiary carbocation. Water is going to attack. Then water needs to clean up to get you a neutral product, and you make an alcohol product in the end. This is the final product. This is not an asymmetric carbon. You don't need to worry about dashes and wedges. There's no carbocation rearrangements. Whew, it's nice to have these as easy examples first. These are both the same first step. That's boron stuff. Boron stuff is going to lead to an H added in the armpit and a BH2 added out there on the dangly arm. Note there's a carbon right there. When you draw reactions like this, don't neglect that little carbon out there. Okay, so the first step is the same for both of these. But then this one is hydroboration oxidation. This is hydroboration bromination. In the right one, you replace the BH2 with a boron. Done. In the left one, you replace the BH2 with an OH. Done. This set of 4 reactions provided me an alkyl halide that followed Markovnikov addition and an alkyl halide that gave me anti-Markovnikov addition. It also gave me an alcohol through Markovnikov addition and an alcohol with anti-Markovnikov addition. Yeah? Let's do a few more. This is acid and water. Acid and water goes through a carbocation. So I'm going to make this carbocation. Water is going to attack it. Water is going to clean up. I end up with an OH connected to that carbocation. We'll draw it up here. It's going to pop up momentarily. But carbocations, sometimes they get a little shifty. Is that carbocation going to shift? Shall that carbocation rearrange? Uh-huh. That carbocation can undergo what kind of shift? A hydride shift to give me a tertiary carbocation. So I end up with 2 alcohol products in that top example because this went through a carbocation. Carbocation, original carbocation made me left product. Shifted carbocation made me right product. Those products, or that product, is both Markovnikov addition. The hydrogen got added to the terminal end of this alkene. Okay, here's mercury. Mercury does Markovnikov as well. So in this bottom reaction with the mercury, we're going to end up with the mercury dangling off over there, and the water will have attacked on the secondary carbon. Then that NaBH4 gets rid of the mercury, and we end up with this. This is my only constitutional isomer. Reaction that went through a carbocation made 2 constitutional isomers. Mercury made 1 constitutional isomer. Alrighty, this guy makes an organoborane. That means the BH2 gets added on the not most substituted side, and the hydrogen gets added on the most substituted side. Hydroboration, oxidation, replace the boron with an oxygen, an OH. Hydroboration, oxidation. Done. So one thing I can appreciate about slides like this, and maybe you can appreciate it too, is it's a nice recap of 3 different ways to make the same functional group. 3 different ways to make alcohols. The carbocation, it's nice because that mechanism I think is probably the easiest, so we kind of like it a lot because of that. But it gets a little shifty sometimes, so watch out for carbocation rearrangements if you're going to choose a carbocation route. The mercury has a complicated mechanism, and let's face it, mercury makes you crazy. So I choose mercury sometimes, but I really choose mercury if I want Markovnikov and I don't want to deal with any rearrangements. The last one, the hydroboration oxidation, I choose that if I need an anti-Markovnikov alcohol. Before we move on to the next set of things to do, this is an asymmetric carbon. Should I create both enantiomers? Yes. This is an asymmetric carbon. Should I create both enantiomers? Yes. This is not an asymmetric carbon. Leave it as is. This is not an asymmetric carbon. Leave it as is. All right, that's your stereochemistry. Synthesis problems. We're going to be asked several different types of questions from tests from now on. Mechanism questions, that's kind of all the stuff we've been doing, drawing mechanisms. Predict the product questions, that's like those last couple of slides we just went through. Draw me the product, including any constitutional isomers and stereochemistry stuff. And synthesis question, propose a synthesis of the following molecules. In order to do well on synthesis problems, in general, you need to know all of your reactions pretty much backwards and forwards. You need to know the mechanisms that they go through so that you can take advantage of the different types of reactions. Did you hear me say that you really need to memorize all? No, I don't really want you memorizing. I don't think it's advantageous to memorize. Can you memorize and survive? Probably. But really, we're supposed to be drawing out common themes in the types of reactions we're learning. Okay, enough of the soapbox. So I have an alcohol that I'm trying to synthesize. And I go back through my catalog in my brain and think, I know 3 ways to make alcohols. What 3 ways? Oh, I think I've seen them recently. Yeah, there are 3 ways to make alcohols. Those 3 ways. Those 3 ways all start from an alkene. In order to synthesize this alcohol, I'm going to need to make it from an alkene. The alkene should probably involve the carbon that has the alcohol on it. That seems to make sense, right? The carbon that alkene, also needs to involve one of the neighboring carbons to the carbon that has the alcohol. So in order to be able to talk about this a little more easily, let me go back up here and put some letters around all of the carbons that are the carbon with the alcohol and the neighboring carbons. So if I were trying to synthesize this thing from that alkene, that's an alkene between carbon A and C. As it turns out, that's the same alkene as between B and C because of symmetry, right? 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 Right. The alkene between C and D is there. So this is C and D alkene. These other red ones were ANC or BNC. Yeah? Okay. So if we're trying to propose a synthesis of that alcohol, we're going to need to start with either the red alkene or the green alkene. One may be a better choice than another. I don't know. Sometimes there is a better choice. Sometimes there are multiple choices that work out the same. If I were to choose the red alkene, does that red alkene have a Markovnikov side? Does that red alkene have a preferred side? Is there one side that would make a better, more stable carbocation? Yes. So if I were to choose the red alkene, I'm wanting to choose a Markovnikov reaction in order to get the product where the alcohol is on that tertiary carbon. So acid and water is a perfect selection for this. Why is it so perfect? Well, because that carbocation is not going to rearrange. It's tertiary from the onset, so I don't have to worry about all the miscellaneous stuff we just discussed. Could I have also chosen mercury to do the same reaction? Yeah, I'll put it here as another choice. When you're doing a synthesis problem, your assignment is not to present to me as many ways possible to make this alcohol. Your assignment is to find one way that's a reasonable way to make this alcohol. So you could do this red path. You could do this blue path from that red alkene, and that's totally legit. You get all your points. From the green path, do I want to make a Markovnikov or an anti-Markovnikov product? I want to make Markovnikov again. So acid and water is a perfectly valid choice. I was thinking, and my hand disobeyed. I was thinking, sometimes you see H2SO4, sometimes you see H3O+, and water, it's the same thing. It's acid and water. It's a perfectly valid choice to make me the alcohol that I want to make. Yeah. Could I have done mercury as well? Yeah. It doesn't matter. I'm not going to draw the mercury reagents over here again, but you could add this green alkene plus the mercury stuff to get there. What can you not choose for either of these? Hydroboration oxidation. Not a possibility, because hydroboration oxidation gives you anti-Markovnikov. Okay, I think I get it. What if I want to make the alcohol on the right? Well, that's going to involve the carbon that the alcohol is on and the neighboring carbon. That means there's only one choice of alkene to make this guy on the right, and it's that alkene. That alkene plus boron stuff will give me hydroxide and peroxide. Boron stuff and hydroxide and peroxide will give me the alcohol I was trying to make. So while we are talking about synthesis, I'm going to explain a couple of weird arrows. I told you, organic chemists, we are crazy about our arrows. So when we say synthesize the following, you often see an arrow like this pointing toward the reactant that you're synthesizing the product from. So this arrow that is so weird down here, this arrow is called a retrosynthetic arrow. A retrosynthetic arrow is two lines with an open end. I know it's crazy. Two lines with an open end. That's a retrosynthetic arrow. A retrosynthetic arrow says comes from or can be made from. So what this line down here says, this alcohol can be made from this alkene. That's a full retrosynthetic analysis of this alcohol. Isn't that fancy? Yeah. So the direction of that arrow confuses a lot of students. This is the starting material, the reactant, and this is the product. A retro arrow points from the product toward the reactant. Retro arrow is weird, I know. So this bottom bit, retrosynthetic analysis. This top bit would be called the synthesis details. That's a traditional reaction scheme where the reactant becomes the product and you add in reagents. We will do a lot of syntheses, so it's helpful if you can kind of get familiar with this stuff early on so that life is a little easier down the line. This is a P. It kind of looks like an R. Propose a synthesis of the following molecules. I don't think you need me to do these for you. I think you're set on doing them on your own. Good luck.